Next, I want to talk to you a bit more about superpositions. The whole purpose of this playlist is not just to give you an introduction without the maths, but also it's really the actual goal is really to kind of give you a tool set so you can then go ahead with your own pace and your own learning. And this is not intended to be sort of the perfect learning material or whatever, but it's more like a list of things that you should know, a list of things that you should keep in mind, and maybe that gives you the tool set to then later on read quantum circuits that you find in papers or in articles, and sort of get a bit more be able to get a bit more hands-on and break down things by yourself and then kind of learn further. So I think this is an important topic. So this is our arithmetic circuit. Let me just clean this and let's talk a little bit about superpositions. What do we know already about superpositions? And there might be more to it, but this is so far what I know, right? So we've got here 5 qubits. You can get into superposition by using Hadamard gates. You don't have to use a Hadamard gate for all the qubits. You just get smaller superpositions. But basically, the idea is you get equal probability of measuring those that particular state. Now, an important thing to keep in mind is that maybe it's going to be easier if I reduce the circuit to 3 qubits to explain what I want to explain right now. So you've got like 8 possible values that you can represent with 3 beats, right? So because we are in an equal superposition in this sense. What's important to note, though, is that so far we've been talking about the probabilities of measuring things, but really, what happens if you just measure 1 qubit? Like, how does this affect the other qubits, right? Because that's really not intuitive. Like, it's really not intuitively. You don't really, from a classical perspective, you're like, yeah, sure, you measure 1, the other 2 stay in an equal superposition, I guess. Which in this case happens to be true, I think. Yeah, because if it's because you have an equal superposition of everything, right? So it's an equal superposition. But maybe let's do this. So let me explain this with an equal superposition and then with a not a full superposition. So you will see the difference. The thing is now, if you measure a 1 or a 0, it basically constrains the space of probabilities or the space of possible solutions you have for these other 2 qubits, correct? Because if you measure that 0 means it's going to write into the bit 0 of this classical register here. But so imagine you measure a 1. This means that now, because you know it's a 1, the rest of your system, right? So this is definitely not existing anymore. This is not existing anymore. Let me mark them. If you measure a 1, right? So this doesn't exist anymore. This doesn't exist anymore. This exists because they have a 0 in their lowest bit state, and you've just measured the 1, so you know that the rest of the possible values are the ones that you have left. So here still, of course, that still means the all the 0 0 0 1 1 0 and 1. But the trick is partial measurement becomes useful when you it becomes tricky and useful at the same time when you don't have those types of superposition. So, for example, what if we had something like this? I don't know, just to give you an example, right? So now, if you measure a 1 here, you know that the rest of your state is going to be in a 0 1 1 1 type of superposition, right? So you know what I mean, right? I mean, it's the thing is when you measure part of your system, you're literally affecting what are the probabilities of the rest of your system. And we talked a little bit about entanglement, right? But this is also kind of related to the same concept. If you've got an entangled state and you measure 1 qubit in being 0, then you know the other one is going to be 0, right? Because you know they always agree. Like that's sort of for one particular type of entanglement. So that's the idea. And actually, you will see that a lot of circuits out there, a lot of actually there's a lot of stuff being done also conditionally here. This means you can do something like, I don't remember how you do that here. I think you must add I think you must, like, for example, this, because you can do a conditional operation, right? As in, apply that. I'm not so sure exactly what this. Okay. I guess it says if C equals to 0, then apply the Hadamard to the qubit 2. That's basically what it's saying. But C is like the entire register. Okay, so you can apply basically conditional operations based on your measurements. I've seen other circuits where they do this a bit differently, where they basically say if for example, if you go here and then if you measure, I think they do something like if you measure, I don't even know how to draw this, but like something like that, right? So, and then that's pretty ugly. And then like an X gate. So, and they say if you measure like a 1, apply the X gate. If not, then you don't apply it. So, conditional operations based on measurements. That's also a thing. Because basically, as I said, they modify the rest of your system. So that's those are important things that you should know about superpositions. It's one important thing. I mean, we've seen that you can do arithmetic with it, and that also you can measure a superposition partially. And a superposition doesn't have to be. That's the most common one. Is like the equal superposition, because it's the one that's used the most. But superposition is any state in which more than one value is probable, and it doesn't even have to be equal. It can be like 10% something and 90% something else. So that's it about superpositions.